असतो सकमया तमसो मा ज्योतिर्गमया मृत्योर्मृतं गमया ॐ शान्ति शान्ति शान्तिः वन्दे मातरम् वन्दे मातरम् सुजलां शुभलां मलयज शीतलां सस्यश्यामलां मातरं वन्दे मातरम् शुभ्रजोत्स्ना पुलकितयामिनी फुल्लकुसुमित द्रुमदलशोभिनी सुहासिनी सुमधुरभाषिणी सुखदां वरदां मातरं वन्दे मातरम् वन्दे मातरम्.
So, welcome everyone. Happy Independence Day to one and all. And I consider it as an honor to host today's event. It's a great privilege for me. And this is the 12th national webinar of Maths Aspirants. Okay. So Maths Aspirants started the webinar series Math Ecstasy, an online odyssey through mathematics during an Independence Day in 2020. And I'm proud and delighted to note that we have reached the 12th one. Okay, and about us, the Maths Aspirants, let me say, I'm going to start with Vinod sir. Dr. Vinod Kumar sir, Associate Professor of TMG College, Tirur, Kerala. He once thought about starting a WhatsApp group for students of his college to discuss about mathematics and to do some problems. And he just initiated the idea and he started the group. And then there were some members of the colleges and more people wanted to join that group. Okay, and friends of these students who were in the group, their friends and more friends. So this WhatsApp group grew, and now we have a big, enormous group of people where there are members all over India and even from outside. So from this WhatsApp group, now we are a community, more nicely, I'll say a family who is connected by mathematics. Now we have webinars like these and problem solving sessions, so many programs, and we are celebrating each and every event related to mathematics and celebrating achievements, helping each other. So many things happening in Maths Aspirants. So when you are a member of Maths Aspirants, you are also contributing to the community, and you are also making the group big and popular. Okay, and this is how we see Maths Aspirants now it is in the newspapers, news, and we have a good impression, and we now can invite big celebrity mathematicians like Krishnaswami Alladi sir. Now we have here. I don't have words to thank him for coming to our today's event. And also we have some teachers in the back of Maths Aspirants, not in the back, I'll say in the stage. Bijumon sir, who is doing all the technical work. And as a pillar of guidance, we have Ambat Vijay Kumar sir, Professor, Emeritus Professor CUSAT, and so many other teachers as well. I can't name each of one, I wish I could, but so many teachers and students and well-wishers, everyone who is working for Maths Aspirants has a contribution to every success of this group. I personally thank and appreciate, and I'm so proud to say this to the big group of people, you. And welcome everyone to today's event. Today we have the national webinar on the topic, the undying charm of the Möbius function, classical results and new variation. And we have a wonderful amazing mathematician here, Professor Krishnaswami Alladi, Professor of Mathematics, University of Florida, US. So he has come here, scheduling his time. It's very early for him to attend the program, but he thought about us and and for us, he's attending too early from there, and we are so thankful for thinking about us. And to say more about sir, we have Professor Vijay Kumar sir. I'm gonna move to the official speeches of our program. But before that, let me mention our speaker. He worked with Paul Erdős, great mathematician, and he also got a PhD at age 22 from University of California. I want to say a big welcome to Professor Krishnaswami Alladi sir, and we all welcome you to this program, sir. Thank you so much for coming to this program. Okay, so we are so lucky and blessed to have such a good webinar. Make use of it, and I'm appreciating all the audience for taking your time to attend the program. And I extend my welcome to Professor Ambad Vijay Kumar sir, Emeritus Professor of CUSAT, and he is there for everything. He's the face in every webinar and every event of Maths Aspirants now, and he is the guidance light of all the programs. And welcome to the program, Vijay Kumar sir. And now, last but not least, we have our Vinod sir. I don't need to welcome him. He's everything of the program. He's the captain of Maths Aspirants. So we are going to start our program with a few words from Dr. Vinod Kumar, Associate Professor, TMG College, Tirur. Welcome, Vinod sir, to the program.
Dear friends, Independence Day greetings to all. Hearty welcome to the 12th National Webinar in the Math Ecstasy webinar series organized by Maths Aspirants groups. Today is very special in the journey of Math Aspirants, as we are blessed to have the great mathematician Professor Krishnaswami Alladi in our platform to deliver this talk. I would like to express my sincere gratitude and thanks to Professor Krishnaswami for accepting our invitation to join with us on this Independence Day. I would also like to express my sincere gratitude to Professor Ambad Vijay Kumar for helping me to get connected with Professor Krishnaswami. I would like to thank all my teachers and well-wishers of Math Aspirants groups. I'm sure that today's session will be really interesting. I wish you all a very fruitful time ahead. Thank you.
Thank you so much, Vinod sir. Now let's welcome Professor Ambad Vijay Kumar sir, Emeritus Professor of CUSAT, Kerala. He's gonna introduce our chief guest, and we are all looking forward to it. Welcome, sir.
Thank you very much. Welcome to Professor Krishnaswami Alladi, who is a mathematician of international reputation. He studied at Vivekananda College, Chennai. While in the B.Sc, he started doing research in number theory on his own. His undergraduate research attracted the giant Hungarian mathematician 𝕤𝕤, one of the greatest mathematicians of the 20th century. And with his recommendation, Alladi went to the University of California in Los Angeles in 1975 on a chancellor's fellowship to do his PhD right after his B.Sc. I'm quite excited to share the information that he got his PhD in 1978 at a very young age of 22 and was awarded the Alumni Medal of University of California for the best thesis in 1978. After his PhD, he held the prestigious Hildebrand Research Assistant Professorship at the University of Michigan and a visiting membership at the Institute of Advanced Study, Princeton. Currently, he has been a professor at the University of Florida since 1986. His research spans several areas of number theory, analytic number theory, probabilistic number theory, CU methods, Diophantine approximations, and the theory of partitions and Q hypergeometric series. In 1997, he launched a journal, Ramanujan, by name Ramanujan Journal, and he continues to be the chief editor now. It was his brain idea to start a Ramanujan Prize at Shastra University, Tanjavur, in the year 2005. And several great mathematicians, Manjul Bhargava, Soundararajan, and many others have received the Shastra Ramanujan Prize over these years. For his fundamental research and his distinguished contributions to the profession, he was selected as a Fellow of the American Mathematical Society in 2013, and he was awarded the honorary doctorate by Shastra University 2 years ago in 2022. With this very brief, very exciting profile, I invite the speaker of this day, Krishna Alladi, to start his lecture on the very special day when all of us celebrate our 78th Independence Day. And in this webinar, in this Math Aspirants group, we celebrate Independence Day by a great, wonderful talk by a great mathematician. So welcome, Krishna, please.
Respected Professor Ambat Vijay Kumar, my thanks to you for inviting me and initiating this, this talk for this Math Aspirants group. Dr. Vinod Kumar, I admire your energy and your foresight in launching such a group and conducting this program on a regular basis. My thanks to you for inviting me. Miss Arjuna, also, I thank you for your kind words and giving us a background as to how your webinar started, the origins of this particular thing going back to this WhatsApp group that Dr. Vinod Kumar started. So I want to thank all three of you. It's also a pleasure for me to give a talk on India's Independence Day, a day that makes us all very proud. I've never actually given a talk on this day. I've given a talk on Ramanujan's birthday many times, but never on an Independence Day. So what I remember about India's Independence Day is we used to get up very early in the morning as schoolboys and go for the flag hoisting in our school. And therefore, I'm not at all worried that I got up that early, because it was in the spirit of Independence Day back in India when I was a school student. So I got up very early today at 4 a.m. for this talk, except there's no flag hoisting, but I'm meeting all of you. But it's a very nice thing. I have modeled this talk as a mathematics lecture, but of course I will explain many things as I go along. But it is at the level of a B.Sc or higher is what I have made this. But if there are school students, I think they will get a decent amount. But if they don't understand fully, then, you know, my apologies. But I've, as I said, done this for B.Sc math students and higher. Okay, so that's why I've done it. Okay, so Dr. Vinod, so now you want me to minimize the
Yeah. Yes, sir.
Okay, let's do that. Let's see what happens. Okay, so now I have this. You're able to see my slide?
Yes,
And
yeah,
you're
yes,
able to
sir.
see it moving?
Yeah, yes, it's moving, sir.
Now you want me to zoom it. So I'll zoom it to, like yesterday, to 200. Is that better? Is this better for you?
Yes, fine.
Okay, good. All right, so I have chosen this theme for a variety of reasons. First of all, the Möbius function is a very fundamental function in number theory, and I can relate it in many ways to things that you may even have seen in school. The second thing is the Möbius function plays such a fundamental role. It is connected to important ideas such as the Riemann hypothesis. So I'll explain what the connections are. But also, since I'm talking to a group of students, these variations that I'm going to emphasize, the ones that I am going to emphasize here towards the second half of the talk, actually go back to my PhD thesis of 1978. And in the last decade, there has been an enormous amount of work coming out of that, results in that thesis, mainly due to Ken Ono and his whole group. So I thought it would be nice to also tell you about some of the very exciting things that are happening now in the last few years. And I'm, of course, very happy that this thesis work of mine has drawn attention. So for all these reasons put together, I chose this this particular title for this lecture. All right. So I also want to thank my own current PhD student, Shravan Sengupta, who actually helped me with this PowerPoint presentation. Okay. So now let me go to an overview of the talk. We'll first start with the definition and fundamental properties of the Möbius function. I will then explain some connections with the Riemann zeta function. And utilizing that, I will actually explain how the prime number theorem, the great prime number theorem, was first proved, and also point out how those ideas shed light on the Möbius function, which has got, of course, intimate connections with the prime number theorem. This is due to Edmund Landau. Then, of course, I will definitely talk about the Riemann hypothesis, what it actually says about the distribution of primes, and also what it says about the distribution of the Möbius function. Then we go to the second half of the talk, where I will first begin with a duality, a very interesting duality between the smallest and largest prime factors of an integer, which I found in 1977, actually, when I was visiting Madras during the summer, and it later went into my PhD thesis. And I will indicate the proof of this and show how these famous results of Landau can be generalized very nicely using this duality. This also involves connections with what is known as the prime number theorem for arithmetic progressions. That is what I've written down here as PNTAP. And that's what gives you some very new results on the Möbius function. And most recent work involves uses of this duality idea in algebraic number fields and Q analogs. So this, as I said, is the work of starting with Ken Ono's group. And I will also mention the most recent work that I'm doing with my current PhD students on higher order duality and its relationship also to algebraic number theory. So this is the overview of the talk, okay? All right, so I'll try to make it as clear as possible in terms of this, because it's really fairly deep in some sense, but at the same time can be explained to non-experts. So let's start with the definition of the Möbius function. So the Möbius function, which is denoted by mu of n, it's an arithmetical function. An arithmetical function means it's a function whose domain is the set of positive integers. Sometimes it's taken to be the set of all integers. And typically, an arithmetical function says something about the integer itself. So for example, you can talk about the number of divisors of a number. So d of n, the number of divisors of a number, is an arithmetical function. Or you can talk about the sum of the divisors. You can talk about the number of prime factors, and so on and so forth. So these are all arithmetical functions. So the Möbius function, to begin with, may appear to be defined in a somewhat artificial way, but actually it turns out to be very natural and beautiful. First of all, mu of 1 is 1. Okay, so we begin with that. Now, if a number has a repeated prime factor, so by the way, p in my lecture will always denote a prime number. So if p squared divides n, that means the number has a repeated prime factor. The Möbius function is defined to be equal to 0. And if the number has r distinct prime factors, the Möbius function is minus 1 to the power of r. So let's take an example. Take a number like 12. 12 has 2 squared as a divisor, so it has got a repeated prime factor. So the Möbius function of 12 is 0. But if you take a number like 6, which is 2 times 3, which is a product of 2 distinct primes, the value of the Möbius function is minus 1 to the power of 2, 2 being the number of prime factors of 6. So minus 1 squared is 1. So the Möbius function on 6 has value 1. Okay. So basically what the Möbius function is doing is, it's looking at numbers which are products of distinct primes. These numbers are called square-free numbers. And if the number has an even number of prime factors, the Möbius function assigns the value 1. And if the number has an odd number of prime factors, the Möbius function assigns the value minus 1. So that's basically what's happening. Okay, so it takes only 3 values, 0, 1, and minus 1. Now, there are 2 fundamental properties of the Möbius function. The first fundamental property is that if I sum the Möbius function over all divisors of a number, you will get 1 at n equal to 1, and you will get 0 if n is bigger than 1. So this sum vanishes for all numbers n bigger than 1. Okay. Now, you may think of this in connection with the binomial expansion that we are familiar from school. So if you have, let us say, a number with r prime factors, n is p1 through pr, then look at the number of divisors of n which have k prime factors, and that will be the binomial coefficient r choose k. So for a number with k prime factors, the Möbius function has value -1 to the k. Therefore, this sum is actually the sum of -1 to the k, r choose k, which is the alternating sum of the binomial coefficients, and therefore is 1 minus 1 to the power of r, and that's why it becomes 0 for numbers n bigger than 1, because every number bigger than 1 has at least one prime factor, so r is at least 1. All right, so now what I want to emphasize is this property, which is given in equation 1, we may think of it as a discrete version of the famous Dirac delta function. So what is the Dirac delta function? The Dirac delta function is 0 at all numbers, real numbers x different from 0, and at the point 0, the height of the function is, so to speak, infinity, in such a way that the area is 1. Okay, so that's the Dirac delta function. So the Dirac delta function is used in calculus or in analysis to select specific values of a function by integration. So for example, if you integrate -infinity to +infinity, f of x delta of x minus a dx, it selects the value f of a. Similarly, this sum here in 1 is often utilized in number theory to select integers with specific properties. So that's why I call it the discrete analog of the Dirac delta function. Okay. Now there's a second fundamental property of the Möbius function. It's called the Möbius inversion formula. What this says is, suppose I'm given an arithmetical function f and little f, and I form a new arithmetical function capital F by summing this little f of d over divisors of n. Then you can recover little f of n from capital F by the sum mu of d capital F of n over d, d dividing n. So, and it's an if and only if relation. So if one sum holds, then the other sum holds. So this is called the Möbius inversion formula, and this is related to what is called inclusion exclusion, which we have also seen starting from school. That is, let's say you have a bunch of properties of members of a set, P1 through Pk, let's say, and then you ask how many members of the set have none of the properties. Then what you do is you take all the members of the set, subtract the members which have at least one of the properties, but then you would have subtracted too many, because what happens to the members which have two of the property? They'll be subtracted twice. So now you add the number of members which have two of the properties, but now you may have added too much, because what happens to members which have three of the properties? They would be counted as in 3 times in this. So you subtract members which have 3 of the properties, then you add members which have 4 of the properties, and so on. So this is something called inclusion exclusion, and this Möbius inversion formula can be connected to this inclusion exclusion argument in combinatorics. So I'll give you an example. Look at the Möbius inversion formula, and let us say you do not know the value or the formula for little f, but you do know the formula for capital F. For example, if little f is the Euler function, which is the number of integers of up to n which are relatively prime or co-prime to n, in this case, it's not difficult to show that capital F of n is n. It's such a simple formula for capital F. Therefore, by the Möbius inversion formula, you have a formula for the Euler function phi of n as summation mu d n over d, and this actually has a product representation. In fact, this is precisely how inclusion exclusion comes in. Okay, so that's just an example. So now let's move on to the Riemann zeta function, and I will give you a connection with the zeta function. So one of the most fundamental functions in analytic number theory, and in fact, I would say in all of complex variable theory, is the Riemann zeta function, and it is defined as zeta of s is the sum of 1 over n to the power of s from 1 to infinity, where this sum is convergent when real part s is bigger than 1. So I want to make one comment here. In number theory, especially in the theory of Dirichlet series, which are series of the type an divided by n power s, that complex exponent is denoted by s. So s is the typical representation for a complex number, and its imaginary part is denoted by a t, and its real part is denoted by sigma. Now, this is what Riemann did, and since he did the most fundamental work here to begin with, we follow Riemann's notation. So we, of course, use x plus iy, but when it comes to Dirichlet series, we use sigma plus it. So this is the Riemann zeta function, and now we know, of course, from school that this function is convergent in s bigger than 1. But now what actually Riemann did was, there is a process in complex variable theory called analytic continuation. So let me give you a simple example of analytic continuation before I go on to explain the slide. We all know that the geometric series 1 plus x squared dot 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 all the way up to infinity converges to 1 over 1 minus x. And this is when absolute value of x is less than 1. So the series representation is valid when absolute x is less than 1. However, 1 over 1 minus x is valid for any complex number, and call it z, let's say, instead of x, which is other than 1, because only at 1 does 1 over 1 minus x become infinity. Therefore, if you define your function f of x to be 1 over 1 minus x and calculate, let's say, its value at 5, you have 1 over 1 minus 5 is minus 1/4. That is the analytically continued value of this series at the point x equal to 5. So analytic continuation is a means of replacing a particular representation of a function, which may be defined only in a limited region, by another representation of the function, which is valid in a larger region. So this is called analytic continuation. Okay. So what Riemann did was, he took that representation of the Riemann zeta function in real part s bigger than 1, which is a half plane, but then he was able to establish what it called a functional equation. And utilizing this functional equation, he was able to extend the values of the Riemann zeta function to the entire complex plane. And when he did that, he found it was an analytic function, which means a differentiable function everywhere, except at the point s equal to 1, where it blows up to infinity. It's called a simple pole. But it turns out that the limit is of s minus 1 times zeta s is equal to 1. So that's a very important work of Riemann. Now, how is this connected to the Möbius function? It turns out that if you look at the Dirichlet series, which is equation 6 below, where the Dirichlet coefficients an are mu n. So if you look at summation mu n over n to the power of s, that actually turns out to be zeta of s. And the way you prove this is, multiply the series on the left by zeta s, and then you use this first fundamental property, equation 1. And when you do that and write it as a new Dirichlet series on the right, all you will get is the number 1. All of the coefficients will be 0 because that Möbius sum vanishes on integers n bigger than 1. That's why this Möbius function is also very important, because its Dirichlet series gives you the reciprocal of the Riemann zeta function. Okay. Now, the person who first studied what we now call the zeta function was actually Euler. He did not use the zeta function notation, but he studied it only for real values of s. And that's what we actually nowadays start with in calculus, where we say summation 1 over n to a certain power is convergent when that power is bigger than 1, and divergent when that power is less than or equal to 1. I mean, this is Euler's observation. And Euler also noticed that when that series converges, it actually has a product representation involving the primes. And so that product I've given in this equation 7. So what Riemann realized, and this was something very fundamental, and that is why this is called the Riemann zeta function, even though Euler was the one who first studied it. What Riemann realized was, it's worthwhile to study zeta s as a function of the complex variable. not only in the half plane where the series is convergent, but also in the whole plane to which it's analytically continued. Because when we do that, we notice from the product formula that information about the primes is encapsulated. It is within that product representation. And somehow you have to pull out information about the primes from this product representation. So that was Riemann's idea. And he had a program to prove the prime number theorem. He didn't actually prove it, but he gave basic directions to follow from which he said the prime number theorem can be proved. So the prime number theorem is a statement about the number of primes up to the number x. Okay, so it is the statement that the number of primes up to x is asymptotically x over log x. All right, so how does this program work? So there is a famous approach here due to Oscar Perron. It's called the Perron integral. So what does this say? You take a Dirichlet series, as we had in equation 4, okay, that series, and our one problem is what is the sum of the coefficients an? So that's the question we ask. Okay? So the Perron integral says that if you say that the function that is given by the sum of the series is called a of s, then s of x, the sum of the coefficients, is actually an infinite integral. It's 1 over 2 pi I of the integral from a minus I infinity to a plus I infinity along the vertical line, x to the power of s, a of s divided by s ds. Now, if you don't follow this particular thing, don't worry. I will give you the actual essence of this argument without getting into technical details in just a moment. So this is the Perron integral formula. But very often what we do is we don't consider the infinite integral. Instead, we truncate the integral at some height t at the top, a plus it, and at the bottom. And typically, we choose a number a which is very close to 1. Because remember, at the Riemann zeta function case, the number 1 was very important. That is the principal pole of the Riemann zeta function. So, and then we choose this a and t optimally to get a good bound on the error. Okay, so this is typically what we do to calculate s of x. Now, the idea was one uses the method of complex variables to move this line of integration to the left. And this is where Cauchy's theorem on complex variables comes in. And this analytic continuation is useful because the further to the left you go, the x to the power of x becomes less. And that is contributing, that helps you in getting a better estimate on the error. So this is exactly how the prime number theorem was proved. So I'm going to give you now some idea as to what the prime number theorem is and how the proof went about. Okay. So what is the prime number theorem? The prime number theorem is the statement that the number of primes up to x, which we denote by pi of x, is asymptotically x over log x as x goes to infinity. So what does that tilde symbol mean? That means if I take pi of x and divide by x over log x, then the limit as x goes to infinity is 1. Okay. Now what is interesting is that even though the Greeks showed that the number of prime numbers is infinite, they never seem to have asked the question, how many prime numbers are there up to a point x? So this idea comes from certain estimates of Euler, but it was really only Gauss and Legendre who conjectured this. So they only conjectured this. But Gauss actually noticed that instead of x over log x, a better approximation will be the integral du over log u from 2 to x. And this is called the logarithmic integral of x. And it's a better approximation. So the prime number theorem, as conjectured by Gauss and Legendre, was proved towards the end of the 19th century, following Riemann's program by two French mathematicians, Jacques Hadamard and Charles de Laval-Poisson, simultaneously and independently using the Perron integral formula and the Dirichlet series associated with zeta prime over zeta minus zeta prime over zeta involving this quantity called lambda n. So I'm going to tell you what lambda n is. So lambda n is the following function. It is log p when n is a power of a prime and 0 otherwise. And why is it so important? Because the sum of the lambdas, lambda d over d dividing n, is log n. See, now this goes back to that philosophy I mentioned earlier between little f and capital F. I said there are many instances where you choose a function little f in such a way that the summatory function, capital F, behaves much better. Here is an example. You take the von Mangold function lambda n, and its summatory function is log n, which is a very nicely behaved function. In fact, it's not just an arithmetical function. You can consider the log x as a function on the real numbers, and it's a continuous function. So it's a number. The summatory function is better behaved. So what this means is, by Möbius inversion, there is this formula for lambda n, and I've done this expansion in equation 14. And if you look at not the extreme sum on the right, but the one in the middle, which where I put a bracket around mu dd dividing n, that sum becomes 0 when n is bigger than 1. But when n is equal to 1, log n, which is log 1, becomes 0. So that term completely drops out. So you get a very beautiful formula for lambda n, which is summation mu d log d. So there is an important connection between lambda n and log n. And that is why the series for zeta prime of s over zeta of s, that is nothing but the logarithmic derivative of zeta. And as you know, the Riemann zeta function has a product representation. And therefore, if you take its logarithmic derivative, you're going to get information on primes. And that is exactly how the prime number theorem was proved originally toward the latter part of the 19th century. So instead of pi of x, they dealt first with psi of x, which is the sum of the lambda function. And then using partial summation, the prime number theorem was proved. But you got it in a fairly strong form. Namely, the error term is x divided by e to the power some constant square root log x, which means it's much smaller than x over any high power of the logarithm. So this is how the prime number theorem was proved. And using partial summation, you end up getting the logarithmic integral of x. Now, why is logarithmic integral of x so nice? Because if you do repeated integration by parts, you actually get a series expansion, x over log x plus x over log squared x plus 2 times, think of the 2 as 2 factorial, or x over log cubed, and then the generic term is n minus 1 factorial, x over log n power x, and so on. And then if you truncate it at position n, the error term is x over log x to the n plus 1. Okay. Now, what way is the Möbius function connected to the prime number theorem? Edmund Landau, a German mathematician, not only a great mathematician, but a very fine expositor, has written books and so on. He showed 2 fundamental connections between the Möbius function and the prime number theorem. Okay, he said, suppose I sum the Möbius function all the way up to x. This sum is little o of x. So little o of x means if you take that and divide by x and take the limit as x goes to infinity, you get 0. So what is Landau saying? What Landau is saying is that the +1 and -1 values of the Möbius function are canceling in such a way that the cancellation is almost equal, that in the very end, the error is small. So that's your little o of x. The second thing that Landau stated was a very striking result, that if you sum the Möbius function from 1 to infinity, mu n over n, you actually get 0. Okay? So I'm going to explain the significance of each of these 2 results. Now, Landau said that these 2 results are elementarily equivalent to the prime number theorem. So what do you mean by elementarily? In number theory, elementary does not mean easy. So if you say I'm working in elementary number theory, a man on the street may think you're working on trivial problems. No. Elementary means you are establishing theorems without the use of complex variable theory. So what Landau is saying is these 2 results can be derived from the prime and number theorem without the use of complex variable theory, and vice versa. If you assume this, you can get the prime number theorem. So that's why these results are so fundamental. Now let us give an interpretation of the Landau result. As you know, the Möbius function is non-zero on the square free numbers. So the question is, how many square free numbers do you have up to x? You have approximately pi squared over 6 times x square free numbers. Now pi squared is nearly 10. So you have 10 over 6, which is 1 and 2, which is that many numbers are square. So the natural, sorry, I made a mistake here. The natural density is 6 over pi squared, not pi squared over 6. So 6 over pi squared is like 2/3, okay? So more than half the numbers in this world are square free. So the Möbius function is non-zero on a set of numbers of good positive density. And on these numbers, the Möbius function takes value plus or minus 1 with equal probability. So you can think of the Möbius function like an unbiased coin in a coin toss if you only look at the square free number. So that's an interesting interpretation. The second is the result of Landau on the sum of the series, the following. Take the series mu n over n power s from 1 to infinity. We know that this is 1 over zeta s. Now take the limit as s approaches 1 plus, that is 1 from the right-hand side, like you would do in calculus. Now the limit of 1 over zeta s is 0, because zeta has this pole at s equal to 1. Remember, we already noted that it has got an infinite value at s equal to 1. So if I interpret this in another way, if I interpret summation mu of n over n equal to 0, which is the right-hand side of 23, I can think of that as the sum of the limit n from 1 to infinity mu of n over n power s, and now interchange the summation and the limit. And when I interchange the summation and the limit, that limit inside is mu of n over n, and that sum is 0. But is that interchange valid? We are dealing here with a conditionally convergent series. We are not dealing with an absolutely convergent series. We are not converging uniformly in s near s equal to 1. So this interchange has to be justified. But this justification is as deep as the prime number theorem. This is somewhat difficult to believe, that when you do this interchange, you are actually doing something as deep as the prime number theorem. A lot of people who don't use so much rigor in number theory or in mathematics, they sometimes do this interchange casually. Non-mathematicians do this casually. But when they do this, they may sometimes be either wrong or they may be using some very deep result. So that's what is happening. Now let me say something about the Möbius function and the error term of the prime number theorem. Since the Dirichlet series associated with the Möbius function is 1 over zeta s, the Perron integral method applies to sum the coefficients mu of n to this function m of x considered by Landau. And therefore, in this particular case, since 1 over zeta s is 0 at s equal to 1, there is no main term. So the Perron integral method actually yields the bound m of x is capital O of x divided by e to the c square root log x. So it's x divided by an arbitrary high power of the logarithm. If better zero-free regions are used, sharper bounds for m of x can be obtained. So the point here is the bounds for m of x are related to the relative error in the prime number theorem. Okay, now let me go on to the Riemann hypothesis. So the Riemann zeta function, as I said, was extended to the entire complex plane using a functional equation, and this was done by Riemann. It turns out that from this functional equation, you can show that the Riemann zeta function at value -2, -4, -6, etc., all these even negative integers, has value 0. These are called the trivial zeros of the Riemann zeta function. Okay, and these are, in some ways, you can say these are related to the poles of the gamma function at the negative integers. Okay, so these are related to that. Now, it turns out that the Riemann zeta function has infinitely many zeros inside a vertical strip, which lies between 0 and 1. That is, you draw a vertical line, the imaginary axis at 0, and draw the vertical line at 1 in the complex plane. In that vertical strip, the Riemann zeta function has infinitely many zeros. This can be proved, but the proof is not easy. Now, in his fundamental paper, his only paper on the Riemann zeta function, Riemann conjectured that these non-trivial zeros will all lie right in the middle of that strip. That is, on the line whose real part is half. So that's what Riemann conjectured. Okay, so this is called the Riemann hypothesis, but he couldn't prove it, right? And the Riemann hypothesis is still unproved, and it is one of the greatest unsolved problems in mathematics. It has several major consequences. One consequence is, of course, that the zeta function will be zero-free in the half plane sigma greater than half, which means if you look at the Perron integral method, remember we were using zeta prime over zeta, and that is the logarithmic derivative of zeta s. In order to define a logarithm, you need a zero-free region. So now, because the zero-free region under the Riemann hypothesis will be having sigma bigger than half, you can move the line of integration to the left up to half plus epsilon, which means you can prove the prime number theorem in the strongest form, that is logarithmic integral of x plus capital O of x to the x plus half, x to the power half plus epsilon. But what does this have to do with the Möbius function? Well, if you use the same Caron integral method, it shows that the Riemann hypothesis is equivalent to the statement m of x is capital O of x to the half plus epsilon for all epsilon bigger than 0. This is a really stunning result. Why? First of all, let me say, there are many who believe in the Riemann hypothesis. In fact, most people believe the Riemann hypothesis. And there are some, I would say relatively few, who do not believe in the Riemann hypothesis. I believe in the Riemann hypothesis. Why? Because of this theorem. Now, why do I believe in the Riemann hypothesis? Because of this theorem. Now, let's understand what this theorem is saying. Think of random walk or a mathematical drunkard. So the drunkard is standing at the origin on the real axis. And at every point in 1 second, let's say, he takes either a step, one step to the right, or he can step one step to the left. But this is with probability half. And think of the coin as a random coin. So you toss this coin, and if the coin appears heads, you go one step to the right. If the coin appears tails, you go one step to the left. And think of this as not just unbiased, that this is like random. Now, if you go to the theory of probability, what it says is that if you take one step to the right and one step to the left with equal probability, and this is random, after x steps, where will you be? You won't necessarily be at the origin. So there'll be some error. But the law of large numbers says that you will be no more than x to the power half plus epsilon after x steps from the origin. So in that sense, this Möbius function behaves, I would say, like a random walk, like a random coin. And I believe that because of this 1 minus 1 property. And therefore, this is a very good reason to believe in the Riemann hypothesis. Okay, now I will come to the new results starting from 1978, and I will tell you what is happening today. So in 1977, actually I noticed it in 76, the paper was published in 77, I noticed two very beautiful and simple identities. So let little p of d denote the smallest prime factor of d, and let capital P of n or P of d denote the largest prime factor. I noticed that if and then I put 1 has no prime factor, so I'm just going to put f of 1 is 0 and just formally define p of 1, little p of 1 and capital P of 1 to be 1. Okay, so if I sum the Möbius function, take any function f on the primes, and f of the smallest prime factor of d dividing n, d bigger than or equal to 2, this just gives you minus f of the largest prime factor of n. So you start with the smallest prime factor, you end up with the largest prime factor. Similarly, if I do that sum over the largest prime factor, I end up with the smallest prime factor. So this also seems to be a sort of a Dirac delta type selection. And I realized immediately that this should have some major consequences. So I'm going to tell you, first of all, let's prove this. As somebody said, every math talk should have one proof. Okay, so we'll have one proof. It's supposed to have one joke. I have not had a joke yet, but you'll forgive me for that. Okay, so let us focus on square free n. We write n as p1 through pr, and let's say p1 is less than p2, less than ... pr. Now look at the sum mu d f of the smallest prime factor of d, and rewrite this in terms of the individual primes pj. So I can write this as summation j equal to 1 to r f of pj, and then the inner sum is summation mu d dividing n pd equal to pj. The smallest prime factor of d is pj. Now, what do you mean by the smallest prime factor of d is pj? That means d can be written as pj times e, where e is a divisor of nj, and nj is the product of the primes from j plus 1 to r. However, note, when you have j equal to r, that is when you have nr, that's a null product, and therefore it's 1. And for nj, nj is bigger than 1 when j is less than r. So what this means is, I can rewrite the sum in 29 as minus, because mu of pje is minus of mu of pj, since I have to write it as mu e mu pj. So this minus summation f of pj, and the inner sum is the sum mu e dividing nj. Now, this is that familiar sum in that first fundamental property. This vanishes whenever nj is bigger than 1 and only selects nj equal to 1. But when it selects nj equal to 1, it selects the prime PR, which is the largest prime factor. So that's where you get minus f for the largest prime factor. And that proves the first duality identity, and the proof of the second duality is similar. So this is really what is going on. Okay, now I'm now going to give you a very striking result, which is a consequence of this first duality. And it may be a little bit hard to believe. Choose any bounded function on the primes, any bounded function. Suppose that bounded function on the primes has an average value over the sequence of largest prime factors. Let's say this average value is c. Then my claim is the sum mu of n, f for the smallest prime factor of n divided by n, is minus c, and vice versa. So this series value for the Möbius function is related to the average value of f for the prime factor. Now this is a remarkable, so this theorem is proved in my paper in 1977 in the Journal of Number Theory. So this was one of the papers that came out of my thesis. This is a generalization of Landau's result. Why? Because we can rewrite Landau's result as summation mu of n over n is minus 1 by discarding the n equal to 1 term. N equal to 1 term is mu of 1 over 1, which is 1. And involving the, adding the term where n equal to 1 gives the value 0. So removing it will give value minus 1. So now, if I choose f of p to be equal to 1, the constant function 1, then this sum from 2 to infinity with f as a constant function 1 is the sum in 32. But if f is a constant function 1, automatically its average over the largest prime factor is 1, because f is constant. So if c is 1, you get equation 31 with value c equal to minus 1 with f equal to 1, and therefore you get Landau's result in the form equation 32. So Landau's result follows. So my theorem is a surprising generalization of Landau's theorem. Okay, but now I'll give you something which is very striking. So you may ask now the question, sir, can you give me examples of functions on the primes which have an average over the sequence of largest prime factors? And the answer is yes. So I'll come to that very soon. Now, I proved, so first of all, there is something called the prime number theorem for arithmetic progressions. What is that? You take any modulus k. So let us say I take the modulus 10. How many numbers are there up to 10 which are relatively prime to 10? 1, 3, 7, and 9. Okay, so there are 4 numbers less than or equal to 10 which are relatively prime to 10, which means all primes, let's say beyond 10, will be in the residue classes 1, 3, 7, or 9, or 10. And the prime number theorem for arithmetic progression says that the primes are equally distributed in these 4 residue classes, more generally for any modulus k. So that's the prime number theorem for arithmetic progressions. So what I proved was, utilizing the prime number theorem for arithmetic progressions, I proved the following theorem. Suppose you look at the sequence p of n of the largest prime factors, not the sequence of primes, but the sequence of largest prime factors, which means for 2 it is 2, then I have 3. Then for 4, the largest prime factor is 2. So I again put a 2. For 5, it's 5. For 6, I put the largest prime factor as 3, and so on. So this is really a sequence of prime numbers, but with repetition, right? Because you are doing the sequence of largest prime factors, and it's repetition with some permutations. But the point is, these repetitions do not destroy the uniform distribution property. So the sequence of largest prime factors is uniformly distributed modulo k. And what is required to prove this would be properties of the function known as the psi function, the number of integers up to x, all prime factors less than or equal to y. This is a function that actually plays a very fundamental role in many problems in number theory, including primality testing and factoring of large numbers and encoding theory and so on. So utilizing this function, I was able to prove my theorem. So what this means is, if I choose my function p to be the characteristic function of an arithmetic progression, then the c is 1 over phi of k, which means I have the prime number theorem for arithmetic progressions here, which I've stated in a strong form. But now, when I go to my distribution for the largest prime factor, I've stated this also in strong form. I don't actually need this specifically for now. I don't want to get into these technical details, but I will mention the following. I get a similar result for the Möbius function, okay? But I'll go to one more slide and tell you what is actually going on. The result that I actually end up getting is that we rewrite Landau's theorem. We already have rewritten Landau's theorem as 2 to infinity mu n over n is minus 1. Now, instead of this series, suppose I look at n 2 to infinity mu n over n, but I look at a subsequence where the smallest prime factor is L mod k, then I get minus 1 over phi of k. This with an error term. So the error term is here. Actually, in 38, I should have 2 to infinity. So why is this so important? The important reason this is important is the original series is minus 1. It's a convergent series. I have now cut up this convergent series into phi of k subseries. And every one of these subseries has equal value. As far as I know, this is the first instance in mathematics or number theory where a convergent series is sliced into subseries all having equal values. It is very easy to take divergent series and slice them up into equal valued subseries asymptotically, because in a divergent series, the contribution is coming in the long-term range. In a convergent series, the contribution is coming from the beginning. It is very sensitive to terms at the beginning. So what we have actually established in this new result is that we have this version of the Möbius function, which is now related to the prime number theorem for arithmetic progressions, just as Landau's theorem is related to the classical prime number theorem. Okay, so I want to now, I will skip the proof of this, and I will also have here, for those who are interested, I can show how this is proved in general for arbitrary f. But now I'll also mention something else that is related to recent work in algebraic number fields. So in 2017, so that I proved this in 1977. In 2017, Ken Ono invited me to Emory University to give a talk to his group of undergraduate students. He had a program called, he regularly has this program called REU, Research Experience for Undergraduate Students, and it's a National Science Foundation Fund program, and it's a program from which he really is able to attract and select many bright students to train. So he called me and said, Krishna, you should give a talk to this REU group. And I chose this work to present to that group of undergraduate students because this was all related to my graduate student PhD thesis. So I said, okay, this will be a good thing for students. Immediately at the end of the talk, he said, this is wonderful. Take your result, put a minus sign on one side, and rewrite it as this sum, Möbius function over n from 2 to infinity, smallest prime factor of n L mod k is equal to 1 over phi of k. And he said, interpret this like an actual density result for primes in progressions. And then he turned towards one of his students, Madeline Locus Dossi, and told her, take Alladi's theorem, you should be able to do something using algebraic number theory. In particular, the Cherepanov density theorem. So, and Dossi did that, and that became one of the main results in her PhD thesis. So I'm going to give you Dossi's theorem. So you have the field of rationals, which is represented as Q. And then you have a Galois extension of Q. That means algebraic field extensions such that it's separable and normal. And you look at the Galois group. And now you take a conjugacy class in a Galois group. Okay, I'm assuming that some of you in the masters know what a conjugacy class is. Maybe in the B.Sc, you may or may not know, but it doesn't matter. Then the point here is that if you look at the sum of the Möbius function such that there is a quantity called the Artin symbol, and we can talk about it later if you want, but it's again getting into algebraic number theory. If the Artin symbol with respect to this Galois extension for the look at the smallest prime factor, and that is equal to C, then the sum mu of n over n will converge to minus of the size of the conjugacy class divided by the size of the Galois group. So I have written it this way so that it is related to my minus 1 over phi of k. But Ken, Ono, and Darcy will take that minus sign and put it on the left-hand side and write it as the size of the conjugacy class divided by the size of G to think of it as a density. So how does this extend my result? Well, it extends my result because if you look at K to be what is called a cyclotomic extension, that means you attach to Q a primitive kth root of unity, okay, called a cyclotomic extension. Then the Galois group can be identified with the group of reduced residue classes modulo K, which I denote by ZK star. And that's an abelian group. So abelian means it's commutative, AB equal to BA within that group. And that means each conjugacy class has only one element. So if each conjugacy class has only one element, this absolute C that you see is 1. And the G is phi of K. So you get your 1 over phi of K, which is Alladi's result. However, I do want to make one comment. What Darcy is proving in proving this result is she first looks at the number of integers up to x for which this Artin symbol with respect to the largest prime factor, that is the one that you're seeing at the bottom at 52, is equal to C. Then that is asymptotic to C over G. So what she's really doing is she's going back to my general theorem. That's really what she's doing. And showing that this little c is capital C over G. So for my general theorem, this other theorem with the little smallest prime factor will be minus C over G will actually follow. Okay, so that's really what Darcy is doing. So in that sense, Darcy's result, I wouldn't say is sort of contained in my general theorem, but at the same time it's not, because she's discussing this in an algebraic number theory setting, whereas I'm discussing that in the regular setting of the setting of the ordinary integers. But there's one more thing I have to say. That is, just as you had the prime number theorem in a strong form, there is a prime number theorem. This is the classical theorem here is called the 𝕎𝕑 density theorem, but Lagarius and Odlyzko have actually obtained the the 𝕎𝕑 density theorem in a strong form, and therefore Darcy is able to get error terms which are better and comparable to the error terms that you get in the prime number theorem for arithmetic progressions, exactly like my 1977 paper, but in this algebraic number theory setting. So this was a new direction in which my duality results were extended. Now, notice, Darcy had Q as the base field and considered an algebraic extension K. Sweeting and Wu in 2019, and I think they also came from Ono's REU program, replaced it with an arbitrary extension L of an arbitrary algebraic number field K. So that was a further thing that Sweeting and Wu did. And then these results have been further extended. But a different extension, and I want to bring Ramanujan into the picture, is the following. Ramanujan considered certain sums which are called Ramanujan sums, CMN. These are the following. You take the primitive roots of unity, right? That is e to the power 2 pi I k over n, where k and n are relatively prime, but then you raise it to the nth power. So look at the nth power of the kth roots of unity. That sum is called CNM. CMN is Ramanujan sum. It turns out that the sum of all the primitive roots of unity is the Möbius function. That's another reason the Möbius function is important. So C1 of n is the Möbius function. So Wang in 2021 took my results and replaced the Möbius function with the Ramanujan sum and proved similar results, okay, density results. So that happened in 2021. And of course, even more general are the most recent results of Wang on global function fields, which is, of course, a very algebraic object. Okay. Now, one other thing that I want to mention is what is called the Q analog. Unfortunately, I should have put an equation here, which I have not. So what is a Q analog? So I'll tell you quickly what it is. Take the integer n, positive integer n. So let's say n equal to 5. Replace the integer n by the quantity 1 minus q power n divided by 1 minus q. Now 1 minus q power n over 1 minus q is equal to 1 plus q squared up to 1 q to the n minus 1. So when I put q equal to 1, or when I put limit q tending to 1, this becomes n, the integer n. Therefore, 1 minus q power n divided by 1 minus q is considered as a q extension of the integer n. So whatever you do with integers n, you can do with this more general function. And it's a very fruitful area where people take things which are familiar in classical number theory and consider what are called their q analogs, which means the classical results will follow by either putting q equal to 1 or letting q tend to 1. So in 2 papers, Ono, Schneider, and Wagner have discussed a variety of q analogs of arithmetic density results in the partition implications, and they have got connections with some of the work that I have talked about here. So that's also one direction. So finally, I want to conclude with this following. In that same paper, I also discussed higher dualities, where I connected the kth largest prime factor with the smallest prime factor, the kth smallest prime factor with the largest prime factor. But here I get binomial coefficients involving the number of prime factors. And this is the Möbius inversion version of that. Well, it turns out that besides my original duality connecting the smallest and the largest, nobody had worked out consequences, well, nobody including me, had worked out consequences of the higher duality. So recently, along with my student, PhD student Jason Johnson, I said, let's look at the second order duality, k equal to 2. And here I proved the following result. We proved first an analog of Landau's result, that 1 mu fn n to infinity is 0, which we rewrite it in this way. And then as a consequence, we slice it up into arithmetic progressions and prove that that's equal to 0. Okay, so this is a consequence of the second order duality. And this is actually technically somewhat difficult because the distribution of the second largest prime factor is very different from the distribution of the largest prime factor. So I want to just mention the most recent work is my PhD student Sengupta, who has actually prepared these slides for me when I gave him the tech file. He and I have extended this for k bigger than 2. And not only that, that's at the bottom. He also has taken the k equal to 2 case and worked out the analog of the Darcy result for algebraic number fields using the Shevcharov density theorem. And I also have worked with another student of mine on more general sums involving the Möbius function and omega n. And this is Yazan Alamoudi. He actually comes from Saudi Arabia. He's a very bright guy, just as Sengupta is. So it's a pleasure working with these young minds on these problems. And I have a whole bunch of references, starting with my early work and recent work that has been done, and all technical papers that need to be studied in order to understand this work. Okay, so that ends my talk. I see some comments coming in the chat, but they're mostly like, thank you and so on. I don't yet see questions there. Should I go to the chat? Or maybe you can see it.
Yeah, not necessarily. Yeah. Hello. There are some.
Oh, one person says, please tell about Diophantine equation results. Yeah. Okay, so let me at the outset say I worked in Diophantine approximations, which has impact on Diophantine equations, but I have not worked on Diophantine equations per se. Okay, so one area where Diophantine equations, I mean, are serious applications of Diophantine approximations and transcendental number theory is, it all started with the work of, well, even before that, but big impetus was in the 70s with the work of Alan Baker in transcendental numbers. He proved what are called effective estimates in what are called linear forms in the logarithms. And using these estimates, it can be shown that certain classes of Diophantine equation have a finite number of solutions. So let me give you an example. There is a very famous problem going back to Catalan, which says 8 and 9 are the only 2 consecutive powers. So 8 is 2 cubed and 9 is 3 squared. So the famous Catalan conjecture is 8 and 9 are the only 2 consecutive powers. Okay. So using Baker's transcendental number theory and results, Tiedemann, a Dutch mathematician, showed that the number of consecutive powers is finite. And he said the number of consecutive, like 8 and 9, all possible solutions, n plus 1 being consecutive powers, the total number of them is finite, and all of them will be smaller than some number, but that number was huge, something like 10 to the 10 to the 500, beyond the reach of computers. So the question is, can you lower this bound to something reasonable so that you can do, let's say, 10 to the 20? And then we can use computers to check numerically up to that point. So that was subsequently done. I forget the name of the person, and Caroline's conjecture was completely resolved. So 8 and 9 are the only two consecutive powers. So these are exciting applications of transcendental number theory to Diophantine equations. Of course, Fermat's theorem is a Diophantine equation. Of course, it has no non-trivial solutions.
I am Aurobindo Ghosh,
Yes.
student of Jadavpur University from West Bengal. Sir, I have a question. You already said that the Riemann zeta function have trivial zeros, which are like that negative even integers.
Correct.
How can we say these are the trivial zeros?
How can you say the series converges there?
The series is convergent.
Yeah. No, the series is not convergent. So I'm very glad you asked this question. The series is not convergent. So that's why I'm giving you this example. Look at 1 plus x squared dot 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 all the way to infinity. You know it is equal to 1 over 1 minus x, correct?
Yes, yes.
But that is only if absolute x is less than 1. Because the series diverges when x is bigger than 1.
Exactly.
But 1 over 1 minus x, you can define it as a function. Suppose I give you a function f of x equal to 1 over 1 minus x. That function is defined at x equal to 5. So the value of 1 over 1 minus x at x equal to 5 is minus 1/4. So you can say that the analytic continuation value of that series is minus 1 over 1/4 at x equal to 5. That doesn't mean the series itself has that value. Now, I want to mention in this connection a story, a Ramanujan story.
Yes.
Ramanujan used to go and show his teachers various results, and mainly he would sometimes like to shock his teachers. And he will sort of try to study the reaction. So one day Ramanujan walked up to one of his school teachers and said, "Sir, I can prove the following results. 1 plus 2 plus 3 up 4 etc. up to infinity equal to minus 1/12.
Yes.
So the teacher said, "This is nonsense. But I'll tell you why this is significant.
Yeah.
Consider the Riemann zeta function summation 1 over n power s.
Yeah.
Formally, put s equal to minus 1. The series is not convergent, it's divergent. You get
Yes.
1 plus 2 plus 3 up to infinity.
Yes.
But now go back to Riemann's paper. Riemann did this analytic continuation of the zeta function. And using that analytic continuation, just as I calculated 1 over 1 minus x at x equal to 5 equal to minus 1/4, using that analytic continuation, calculate the value of the Riemann zeta function at minus 1.
Exactly.
And you get minus 1/12.
Exactly.
The beauty is, Hardy said Ramanujan did not know complex variable theory and analytic continuation. But he wrote down a value of the Riemann zeta function at minus 1, right, which is the 1 plus 2 plus 3, without knowing analytic continuation. So it is not the value of the series, it is the analytic continuation value.
Exactly.
Okay, so that's the answer. So when you do that at minus 2, you'll get 0. Minus 4, you'll get 0.
Yes. Thank you, sir.
So now one other person had a question. They raised their hand. Saloni Raj.
Hello, sir.
Yes.
Good evening, sir. I'm Saloni Rai from Savitribai Phule Pune University. Sir, I would like to
Okay.
know why do some people do not believe in the Riemann hypothesis? Is there any contradiction to this theorem? Just like you have given the statement to in the support of the Riemann hypothesis. So why do people do not believe in the Riemann hypothesis?
Oh, so let us say you don't believe in the Riemann hypothesis, and let us say you assume that there is 1, 0 not on the real line, on the half line. Okay.
Yes, sir.
So it's away from the half line. So no, see, these zeros are symmetrically located. So if there's 1 0 to the left, you'll have another 0 to the right.
Yes.
So what that would mean is that the size of m of x will not be as small as x to the half plus epsilon.
Sorry, sir. Size of?
It won't be as small as x to the half plus epsilon. Maybe it'll be like x to the 2/3 or something. But we are not able, nobody has proved that.
Okay. Okay.
So nobody has proved or disproved the Riemann hypothesis.
Okay. Okay. Thank
Yeah.
you, sir.
Hello, sir.
Yes.
Am I audible?
Yes.
Sir, first of all, it was a very wonderful talk.
Thank you.
And secondly, I would like to introduce myself. I am a third-year undergraduate math student at VIT Vellore. I have two questions.
Yes.
First, I would like you to repeat that Perron's and Riemann's approach for the prime number theorem. Like you told about that, how he uses the Perron's integral and substitutes like a is equal to 1 plus 1 over log x to get to like to extend it to the left of that zeta, that sigma greater than 1.
Yes.
So could you repeat that again?
Okay, so Riemann actually did not do all that. I mean, that's due to Oscar Perron. Okay.
Okay.
Riemann only said that using this, you can get the prime number theorem. He gave, of course, he was a master of integration. But specifically to these number theoretic questions, there were gaps in Riemann's arguments. And he knew that. He did not claim to prove the prime number theorem. So it's only later authors who did it. So Perron gave this general integral formula that you can use this to calculate some of the coefficients of a Dirichlet series. Then what happened was Hadamard and De La Valle-Poisson said a natural Dirichlet series will be zeta prime over zeta because that is related to log n, which is the sum of the logarithms of the primes that divide n. So there is a prime number information there. So they applied the Perron integral formula to zeta prime over zeta. But then what means is you want to move the integration line to the left. You can't move it all the way up to half because if you move it up to half, you have the Riemann hypothesis, which is unproved. So they said, I don't have to move it up to half. If I can show that the Riemann zeta function has no zero free regions. So you see what I'm doing, my left is to your right. So I'm going to turn, okay? So this is the one line. You're able to see?
Yes, sir.
Line. Here is S equal to 1. They just moved a little bit to the left and closed it. And they were able to show that the Riemann zeta function has no zeros, just a little bit to the one line. And the amount of penetration was 1 over log t. So in other words, if you go to height t, you can penetrate, you can go to 1 minus 1 over log t. That's a rather difficult result to prove. So they proved that there are no zeros there, and they proved bounds on zeta prime over zeta. So they moved the line of integration using Cauchy's theorem to that, concluded the thing, and then they chose t optimally. And the optimal choice of t was e to the root log x, when you take two terms and put them equal. That is how you got the prime number theorem in that strong form at that time. By the way, in an analytic number theory course, I proved the prime number theorem, and it takes something like 3 weeks. So you just don't do it in one day. I mean, there are a lot of auxiliary results, complex lemmas from complex analysis, various things that you have to use to prove this.
And my second question was, like they told in the introduction, you worked with 𝕐𝕗 as an undergraduate. What was that problem that was it related to that 1977 thesis?
Well, okay. So there is a yes and no. I'll tell you what happened. The Erdős was not related to the 1977. So I was a student at Vivekananda College, and I was doing some work on my own, number theory. I first started with Fibonacci numbers. And then everybody said, that's wonderful, but look at something a little bit more deep and then study number theory. So I took home the book of G.H. Hardy and E.M. Wright, Hardy and Wright's Introduction to Number Theory. Now, my father at that time was the director of the Institute of Mathematical Sciences, IMSc as it's called now, in Madras. So, I got this book from the library and I started reading it. I noticed that there was a literature on the sum of the divisors, sigma n, going back to the Greeks, the perfect number problem. There was a discussion in the book about the number of divisors, that is the Dirichlet divisor problem. There was a discussion in the book on the number of prime factors, that omega n that I've used in this talk, that is due to Hardy and Ramanujan 1917. Now, what is missing? The sum of the prime factors. So, I was a young undergraduate student. So I told myself, why not discuss the sum of the prime factors of a number? So, pardon my teenage pride, I call that function A of n, A for Alladi. So A of n is the sum of the prime factors of a number, including multiplicity. And A of n has the property that A of n, nm is A of m plus A of n. So it's like a logarithm. And the other property is that the number of solutions of the equation A of n equal to m is the number of partitions of m into primes. That comes from the fundamental theorem of arithmetic. So I said this is a very interesting function to consider. So I started proving theorems on this function. And at one point I got stuck. I wanted to show that I got the average value, but I couldn't get the normal order. Then everybody said, you must write to Paul Erdős. But how do you write to Paul Erdős? He's traveling all around the world. So they said, write to the Hungarian Academy of Sciences, and they will redirect your letter. So I was in the final year of B.Sc, 1974, October or something. I wrote a letter to Paul Erdős to the Hungarian Academy of Sciences. Promptly, in about a month, I got a reply from Erdős saying, the results are very good, and I would like to meet you. I am coming to Calcutta to the 100th anniversary conference for Mahalanobis, the founder of the Indian Statistical Institute. That's going to be in December. Will you be at this conference? So I said, I wrote back saying, my paper, undergraduate paper, has been accepted for presentation at this conference in the student session, 15 minutes. But I won't be there. My father will be there. He was giving a 1-hour address. And I told my father, will you present my talk? I mean, this was last year at B.Sc, so I couldn't afford to miss classes. So he said, I'll present your talk, but I will not take any questions. Okay. So I mentioned to Professor Erdős that my father will be presenting my work. So what is interesting is, he does not attend my father's lecture because in the theory of probability and statistics, he attends my father's presentation of my work in the student section. So that tells you how interested he is in encouraging young people. So after my father's talk, he goes up to my father. By the way, one of your guys here in the chat said, please imitate Paul Erdős, and I will imitate him for you. So he goes up to my father and he says, while I am very pleased to meet you, I would be much happier to meet your son. My father says, well, my son is in Madras and, he's not here. So then Erdős says the following. I mean, unbelievable. He says, my next stop is Sydney, but I have 1 extra week here at the ISI, Calcutta, but I've finished all my work. Why not I come to Madras on the way to Sydney? I'll reroute my trip. I'd like to meet your son. Can you believe anybody else doing this? So he comes to Madras. I meet him at the airport. I was very nervous. I'm meeting a great mathematician. I was very nervous. And as soon as he meets me, he says, "Hello, do you know my poem about Madras?" I said, "No." He says, "This to the city of Madras, the home of the curry and the dal, where Iyers speak only to Iyengars and Iyengars speak only to God." So I said, "Sir, I don't know this poem." So he said, "This is modeled along a poem for Boston. This to the city of Boston, the home of the bean and the cod, where the Lowells speak only to the Cabots and the Cabots speak only to God." Now, why I mention this poem is, as soon as he said this, I was at ease. I mean, he was a great mathematician. He was not putting airs. It's, a lot of mathematicians, top mathematicians are arrogant. He was not like that. It was so easy to talk to him. So I was with him. He gave a talk at Mad Science. He gave a talk at the Ramanam Institute. I attended both talks. And one day we were walking along the Marina Beach. And I told him, "Professor, I'm able to prove these results for A of n, but I'm not able to prove that it has got a normal order." Then he stopped for a moment and he said, "I know why. Because in the sum of the prime factors, the largest prime factor dominates. And therefore, since the largest prime factor does not have a normal order, you are not able to prove this result." Then immediately I asked him the following question. If the largest prime factor dominates in this sum, if I remove it, will then the second largest prime factor dominate? If I remove now the second also, will the third largest dominate? And so on. He turned towards me and said, "That's a very nice question. Why don't you prove that theorem?" Then he gave me some references, including the psi of x, y, and so on. So I studied all that for the next few months, side by side to my B.Sc exams. And by the summer, I had proved that theorem. Of course, I communicated it to Erdős. She made some minor corrections, and that became our first joint paper. So that's how the joint paper with Erdős came about. And later I had 4 more, but that was the beginning. And when he was in Madras, he asked me, "What is it? Where do you want to go for graduate study?" I said, "I've applied to several places." He said, "I will write only one letter and you will get admission there." So he looked around my places and he said, "I'll write to UCLA, where there is Professor Strauss. He will allow you to work on your own. At the same time, he will guide you." So he wrote to Professor Strauss, I think first week of January. That was when he was in Madras. I got my admission to UCLA on January 15th, and I got my Chancellor's Fellowship to UCLA in March. So it's all due to Erdős. So,
Okay, I have an observation to make. I too was fortunate enough to shake hands and meet Paul Erdős
yes,
at Budapest Alfred Rennie Institute.
yes,
I will share a small story. 1 second.
please.
I gave him a picture postcard containing the Kathakali. Kathakali is a classical dance drama of Kerala.
Yes.
So Paul Erdős started asking me questions about Kathakali and this particular character. But he knew more than me about Kathakali. I was totally ignorant about Kathakali. And we had a long chat for about an hour because I was also giving a talk there.
I see. All right.
Now I have a question on the Riemann zeta function.
Yes,
Riemann zeta function initially defined as an infinite series.
yes,
It also admits a product representation
correct.
in terms of powers, primes. And the infinite product converges if and only if the corresponding sigma log converges, isn't it?
Correct. So you can actually show the convergence of the product even on the one line to a certain value.
Sigma equal to 1.
Yeah, you can. But it's not related to the series. So there is a slight difference there. But
So
you can't do it to the left. But you can't go to the left of one.
Yeah. But still that distribution of prime numbers remains an enigma, isn't it? Even
Yes,
with infinite product representation.
Beyond that little penetration, we don't know.
Yeah. And in fact, recently in 2019, there was a paper by Michael Atiyah saying that he has a proof of Riemann hypothesis.
Right, he gave a talk in Heidelberg at the some laureates forum.
Yes, yes.
And various people looked at it, so they didn't think much of it. I mean, Atiyah is a genius. He got the Fields Medal, but in later years, you're not the same person, just as tennis players become weak and cricket players retire and so on, just like that. Our mind is no longer as sharp.
Okay.
That's why it's important to talk to students.
Yeah.
That's why these things are important.
In fact, Surya was here last week to give a talk on an endowment of mind.
Oh.
And he spoke mostly on Ramanujan sums.
I see. Okay. Good. It looks like 2 more have raised hands.
Yeah.
Thank you, sir, for your answer.
There is one person, Kirtana, and then 3 more.
Good evening, sir.
Yes.
So my question is actually a bit more general and less to do with mathematics. I hope that's okay. So first of the story about you getting into UCLA, it was really amazing. And this talk was very inspiring for me actually, because I'm a 3rd year B.Sc mathematics student, and you being able to do PhD directly, that in a foreign university, it's nothing short of a big deal. And I also love number theory, so that's also amazing. My question was that when you went to UCLA, there must be certain constraints like accommodation, cost of living, and traveling, like coming home, going back there, maybe during vacations and stuff. So I guess what I'm asking is, were you on any scholarship? Were you being funded by them?
So the thing is, I applied to several places, UCLA and Harvard. At UCLA, I got the Chancellor's Fellowship. That is the most prestigious there, and it straight away gave me 4 years support. So I had funds there, which took care of my stay. Harvard, I got admission, but they said they were going to decide on support much later. So I didn't want to wait. And also Erdős's letter was to UCLA, so I took it. So I had no problem in terms of just living there. I wanted to live in the graduate student dormitories, the hostel. But UCLA had a very strict, California had a very strict liquor law that only students, I think 21 and above at those days can take liquor. I was and still am a teetotaler. I don't take any liquor, but I was only 19 at that time. So I told them, my age is 19, but I'm a teetotaler. And they said, no, we can't take chances. So I stayed in the undergraduate dorms for the first year. And that was quite rough, meaning rough not for me because they were very noisy and, playful people and so on. Then I moved into an apartment. But I had enough money to live comfortably. But I came to India in the summers. My father paid for my ticket. So I came to India. But now I think student stipends are much more. So they can go. But also university support is there if they go for a conference.
Thank you, sir.
Yeah, thanks.
Hello, sir. Myself,
Yes.
Sagar Mondal. So I have 2 questions. That what is the most beautiful applications of modular forms up to now? So this is the first question. The second question is that what is the future of the study of modular forms?
Okay. So first thing is, I am not an expert on modular forms. So regarding the future and what directions, it should be directed to someone who is really working in modular forms, somebody like Ken Ono. But I can tell you a beautiful application of modular forms is, for example, in the partition function, Ramanujan conjectured several congruences, divisibility properties. And like the partition function, there are other partition functions, which have these divisibility properties. And the theory of modular forms can be used very beautifully to establish these congruential properties. That's one very exciting application of the theory of modular forms.
Okay.
Okay?
Sir. Thank you. Sir.
Yeah. Any other questions?
So, my
Yeah.
name is Arya, and first of all, I would like to thank you for this wonderful section. And I think it's really blessed to us that we are attending your lectures and all. And also, I would like to thank Vinod sir for conducting such a wonderful section. And thank you, sir.
Thanks. It says two more have raised hand. Yeah, Praveen. Or who?
Hello, sir.
Riya. Yeah. Yes, go ahead.
Hello, sir. Good evening, sir. So first of all, sir, I want to introduce myself. So myself, Riya Yadav from University of Allahabad, Uttar Pradesh. Sir, knowing your journey is a true inspiration to us. So we got to learn a lot from this session, and this was a very interactive session, sir. Sir, also, I want to express my heartfelt gratitude, sir. You have, sir, for your precious time and knowledge that you have shared with us. Thank you so much, sir. And
Thanks.
sir, it's a beautiful and powerful reminder that with patience and hard work, anything is possible, sir. Your extraordinary journey is a true reminder to us and gives us a lot of inspiration, sir. And
Thank
at
you.
last, I also want to extend my heartfelt thanks to Vinod, sir, for giving us the privilege to meet with such great and extraordinary, esteemed personality. Thank you so much, sir. At last, happy
It's my
Independence Day,
pleasure
sir.
to
Thank you so
address.
much.
Thank you. It was a pleasure for
so
me
much.
joining this group.
Thank you so much.
Greetings, sir. My name is Praveen Casey. So, sir, you said you started research while you were on the third year of B.Sc. So,
No, actually, end of PUC. Third year was when I wrote to Erdős.
yes, sir. So, can you give us advice on time management and how to go ahead of the system and all? What would you be your general advice to graduate and undergraduate students?
Well, so number one, you have to pay attention to your classes and your exams. I have met some students who have come and said, we don't like the syllabus, I'm doing all this work and so on, and then they are kind of falling low in their grades. You cannot be like Ramanujan, who dropped out of school and was picked up by, G.H. Hardy. You have to focus on your exams. What about time management? Well, I was doing things, on weekends, after I finished my schoolwork. I mean, there is plenty of time. Your school and college work, if you do on a systematic basis, I don't think require beyond the class more than a few hours a day. So you have a few more hours left when you can work on your own on various problems. So I think time management can be done that way. And what about vacations? Your summer vacation, your Christmas breaks. You can enjoy, and at the same time, you can work. I don't believe in, goofing off for the entire vacation. Even now, when I go with my family on vacations, I mean, I work a few hours each day. So that's your time management.
Sir, associated to that, does University of Florida offer any online internships during the month of April, May, June, etc.?
I don't think there are online internships. I think internships probably require you to be physically present here. But I think once you are here and you do research, it's possible for you to go away as long as you maintain contact with the professor. But I don't think you have just an online internship. I don't think so. I may be wrong.
Okay, sir. Thank you.
Okay, so we have some more hand ups. We can have 2 to 3 conversations, I guess.
Sir, hello, I'm Saloni again.
Yes.
Sir, One thing was in my mind that if the zeros are lying in the strips of the zeta function, so can we define some algebraic operation over that, and then we will be able to prove that it is in the strip or any zero is lying outside the strip. Because if
Well,
all the zeros are lying in the strip,
yeah. So to answer your question, there are approximations to the Riemann hypothesis. For example, there are theorems which say that if you choose an epsilon neighborhood, then you have plenty of zeros around. We know, for instance, there are infinitely many zeros on the line, half.
yes, sir.
We also know, we also know that among all the zeros, if you, let's say, go up to a point T,
Yes, sir.
about more than 1/3 of them will lie on the half line.
Yes, sir.
We know that if you go half plus epsilon, half minus epsilon, then almost all the zeros will lie there. So the zeros that lie outside are very rare. So there are various results like this which can actually be used to prove other things. These are called zero density results, various other results. So these results can be used to prove results on gaps between primes, things like that.
Okay, sir. Sir, I want to ask one more thing. Can we access your PPT from any platform? Can we have access of your
Excuse me, what is
PPT from any platform? Sir, PPT which you have presented over here, can we have the access over
you
it
mean
after this?
what is Excel? You mean the slides?
Yes, sir. I
Yeah, but
posted
I
it
sent the
after.
slides to I sent the slides to Dr. Vinod. Dr. Vinod has my slides.
Okay, sir.
Yeah.
Saloni, you
We
can
can share
contact
it with the recorder. Yeah.
Vinod, sir.
Yes, sir. We can share it with the recording of this lecture.
Yeah. Only thing is, notice that there is the pi squared over 6 is 6 over pi squared.
Yeah, if possible, you may send the corrected one as well. If possible.
Then wait for 24 hours because I'll contact send to and send it.
Okay, sir. No issue. Okay, sir.
Okay. Because today I'm traveling. After this, I'm leaving over Atlanta.
Okay, sir.
Arjuna, I think there are 2 more hands. After that, just go for the
Yes. Okay. So with the restriction of time and very precious time of our chief guest, we're gonna restrict to the last 3 hand-ups. So I think Gayathri was trying to speak earlier. Gayathri?
Hello, sir. I am Gayathri. I'm doing M.Sc from NIT Calicut. The talk was incredible, and I'm really happy and blessed that I could able to attend this webinar. And you have shared a lot of important information, which we are really grateful. And thank you so much for spending your valuable time with us. And thank you, Vinod, sir, for conducting this session for us. Thank you so much.
Thank you.
Okay, Shikha?
Good evening, sir. I'm Shikha. I'm a PhD scholar from IIT Mandi. So we are fortunate that we are able to attend your session and able to learn from your experiences. So I would like to know more about your PhD journey and your suggestions for all the PhD scholars present here.
So I had a very fruitful time at UCLA. Professor Strauss was a remarkable advisor. By the way, he was the last student and assistant of Albert Einstein. He originally worked in theory of relativity and later moved on to number theory because of contact with Paul Erdős. So his door was always open. My office was right across the corridor from his office. So anytime I had an idea, and when his door was open and he had no visitor, I would crash into his office and offer him, I'll say, here's something I've done, whatever it is, and really discuss with him. So I think one very important thing is that to have a real good rapport with your PhD advisor. Because sometimes PhD advisors can be aloof. That's not very helpful. Sometimes very important PhD advisors can be aloof. But it's so much better if there is, open door policy. And that was something that I had at UCLA, not only with this professor, but many other professors. I used to attend the weekly colloquia every week. Whether or not you understand the lecture, attend colloquia, because you will get something out of it. You first of all understand the landscape of mathematics, so you know how various subjects are moving. So I would attend a colloquium in algebraic geometry. I'll attend a colloquium in abstract in group theory, just to get an idea how the field is moving. And I think this kind of overall background is useful. And I also had a very good academic social life. So after the colloquia, there would be usually the host of that speaker would have a party at his house. And I would go, because there you could meet and talk to professors in the department in a very relaxed setting. Talk means what? We're not going to talk about Paris Olympics and the medal. We talk mathematics in a relaxed setting. Okay, then they will tell you some things and so on. So all this is overall useful in your mathematical development. So I think, I would say graduate study in the US provides that opportunity. I'm not saying it doesn't provide that opportunity elsewhere, but here we have this. In addition, I was a teaching assistant also for 2 years. So I taught calculus, I taught differential equations, I helped other teachers. So I gained a teaching experience because of that. So you have teaching and research go hand in hand. I think that's a good thing. And of course, a top place means you have lots of really eminent visitors giving talks and so on, and that is a big boost. Who can't compare. Going to a course and learning is one thing, but then listening also to a world leader is something. But of course, in the top US universities, many of your professors are themselves world leaders. So, like if you're in Caltech in those days, Robert Feynman or Richard Feynman will give the talk, teach the undergraduate physics course. So that opportunity is there.
Thank you, sir.
Sir, Shikha did the promotional video and Unnati is also here. Unnati, please turn your video on.
Oh, you did the promotional. Okay, good. Thank you.
Yes.
Okay, so
Yeah,
I think we had a good number of questions.
Yeah. Arjuna?
Okay, so with everyone's permission to end today's event, I'm gonna call for a vote of thanks. But before that, personally, I feel so happy to meet Professor Krishnaswami Alladi. Sir, you made our day. Really,
Thanks.
it was a profound talk. You added lots of mathematics. I'll say most of the things I couldn't follow, but it was really enjoyable. And like you said, Paul, this made you at ease. You made us at ease.
Thank
You are such a great person, but this many people interacted with you just because you were so humble, you're so kind, and you were really open and shared all your experience with such a honesty. So we really appreciate
Thank
you, sir. And
I
so
enjoyed
much-
meeting. It's always nice to talk to students, enthusiastic students.
Thank you so much, sir. Now, officially, to say the vote of thanks, I'm gonna invite Dr. Rosna Paul, Graz University of Technology, Austria.
Thank you.
From
Dear
Graz.
participants, sorry.
Are you from Graz?
I'm originally from India, but I completed my PhD from Graz. Yes.
Oh, I was there last summer.
Oh, really? I'm from the TU Graz, Technical University of
Yeah,
Graz.
I was visiting Robert Tishy.
Ah, okay.
Anyway, go ahead with your vote of
Yes.
thanks. Yeah.
So dear participants, Dr. Bijumon sir and our distinguished speaker, Professor Krishnaswami Alladi sir, as we conclude this remarkable session, it is my privilege to extend a heartfelt vote of thanks on behalf of the Max Aspirants group. First and foremost, our deepest gratitude goes to Professor Krishnaswami Alladi, sir. We are particularly grateful for the clear and engaging way in which you discuss the classical results related to Möbius function, including its links to the prime number theorem and the Riemann hypothesis. These topics, often considered complex and abstract, were made accessible and clear through your expert explanation. Sir, your reflections on your incredible journey in mathematics have truly been an inspiration to all of us. Your dedication to advancing the field of mathematics and your contributions to the global mathematics community are fabulous. Thank you, sir, for sharing your time and knowledge with us today. Thank you so much.
Thank you so much. And please convey my regards to Professor Tishy if you happen to see him in the hall.
Yes, I will.
Okay.
Then I would like to express our sincere thanks to Dr. Bijumon, sir, for graciously introducing Professor Alladi, sir, and setting the tone for today's session. We are deeply grateful for your support and presence. Thank you, sir. Then a special
Rosna
note of,
is my master student.
yes, I was from CUSAT, and I did my master's and MPhil from CUSAT and under Bijumon, sir.
Wonderful.
Then a special note of appreciation goes to Ms. Arjuna for her excellent anchoring throughout the session. Your energy and professionalism kept the event flowing smoothly and ensured that everything ran on time. Thank you, Arjuna. And then I would like to extend my thanks to Dr. Vinod Kumar, sir, the founder of Maths Aspirants Group, whose vision and passion for mathematics have brought us all together. This is through his tireless efforts that we continue to create such enriching platform for learning and growth. Thank you, sir. And then a big thank you to Ms. Unnati and Shika for creating the promotional video that brought attention to this event. Your creativity and hard work played a crucial role in making today's webinar a success. I would also like to thank the rest of our organizing team for ensuring the smooth execution of today's event. And finally, to our participants, thank you for your enthusiasm and for making time to join us on this special occasion. Your encouragement and engagement, curiosity are what made these sessions truly meaningful. And as we conclude today's session, I encourage all of you to stay connected with Math Aspirants Group. Let's continue to explore, learn, and share our passion for mathematics. We look forward to welcome you to our future events where we can dive even deeper into the wonders of this beautiful subject. Thank you all once again and have a wonderful day ahead. Auf Wiedersehen.
Thank you.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाधा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय जय जय